Hi everyone, thank you again for joining us for a third talk before the break. The next talk is from Cvetanka Eftimoska on data preprocessing for machine learning using Python. Hi Cvetanka.
Hi.
The data preprocessing is a crucial step in machine learning, and it's very important for the accuracy of the models. Most real-world data has noise, missing values, and data that is just unusable because of formatting. Hence, Cvetanka will talk today about data preprocessing and how to deal with these problems. Cvetanka, you may take it away.
Thank you. I'm really happy and glad that I'm part of this conference. I currently work as a senior technical consultant at Interworks. Some of the technologies that I have worked on are relational databases and SQL, developing ETL processes and data warehousing, C# and .NET, desktop and web applications, working on BI solutions in Tableau, and so on. My main focus at the moment is machine learning, deep learning, and artificial intelligence. As part of the Interworks team, our goal is to increase the data efficiency. We are focused on extracting the most important and valuable information that are contained in the data. And as part of this, we are focused on machine learning and how we can use these algorithms on a daily basis to improve the process of extracting and analyzing the data and provide great value on the projects that we are working on. That is why today I'm going to speak about the data preprocessing techniques that can be used to clean the data and use it in a machine learning model. I would like to say a couple of words about the company. Interworks is a global multidisciplinary integration consultancy, and it is a company that is focused on strategy, data management, analytics, infrastructure, and growth enablement. Our mission is to create outstanding values for our customers and to empower them to outsmart their competition. We bring a unique combination of a proven engagement model, high quality, consistent development process, deep technical expertise, world-class infrastructure, and a great sense of teamwork. We work with the three most popular integration tools, SnapLogic, MuleSoft, and TIBCom. We have a big quality assurance department, and also we have expertise, knowledge, and resources in artificial intelligence, big data, machine learning, Microsoft mobile development, AWS cloud data management, and so on. Our clients are located in USA and Europe, and you can find us in Bitola, Prilep, Skopje, and Amsterdam. Interworks is a company where you can thrive and grow both professionally and personally, a place where you can freely share your mistakes, opinions, and knowledge. That will be some short introduction to the company. The goal of the presentation today is to show how we can define a machine learning model. First of all, I will define what machine learning is, what is artificial intelligence as well. And as I mentioned earlier, the focus of the presentation will be the data preprocessing. There are a lot of methodologies and concepts that can be used, but in this example, we will see some of them. For example, we can see how we can handle missing values, how we can deal with outliers, multiculinarity, how we can deal with categorical features, balance our data set, standardization and normalization, how we can shuffle the data, and the last step will be splitting the data into train and test set. At the end, we will see how we can evaluate the model and how to extract the model consumptions. Artificial intelligence is a science like mathematics or biology. It studies ways to build intelligent programs and machines that can creatively solve problems, which has always been considered a human prerogative. Machine learning, on the other side, is a subset of artificial intelligence, and it provides the system's ability to learn and improve from experience. Deep learning is a subset of machine learning, and it uses the neural networks to analyze different factors with a structure that is similar to the human brain. Early classification of machine learning approaches divided them into three broad categories, depending on the nature of the signal or feedback. Those three categories are supervised machine learning algorithms. They build a mathematical model of a set of data that contains both the inputs and the desired outputs. Unsupervised machine learning, on the other hand, algorithms take a set of data and the data contains only inputs, And these machine learning algorithms try to find structure in the data, like grouping or clustering of data points. And the third category is reinforcement learning. This is a computer program that interacts with a dynamic environment in which it must perform a certain goal. For example, driving a vehicle, playing a game against an opponent, and so on. Machine learning has gone through a lot of developments and is becoming more popular day by day. The process is composed of several steps. First, we need to collect the data. Then the next step is preparation of the data, and this includes some data preprocessing transformations that will improve the model. Then the next step is training and testing the model, and the last step is extracting the model consumptions. So why data preprocessing? Why did they chose to speak about this today? So this is because data preprocessing is a crucial step in machine learning and is very important for the accuracy of the model. Data contains noise, missing values. Sometimes it is in an unusable format, and that's why we are preprocessing all the data. The goal of the preprocessing is to get more meaningful data and data that can be trusted. These techniques allow us to transform the raw data into clean and usable data set. The libraries that I'm going to use in the example are Pandas. Pandas is a package that provides fast, flexible, and expressive data structures. The next library is scikit-learn. Scikit-learn is a library that has many unsupervised and supervised learning algorithms. StatsModel is a package that allows users to explore data, estimate statistical models, and perform statistical tests. Matplotlib is a library for plotting, and Seaborn is a library for making statistical graphics in Python. Also, I will use the library FancyImpute for imputing missing values using mice. And also, I will use the library IMBlearn for balancing the dataset using Smooth. The first step is exploring the dataset. In Python, we can use the method describe, and by using this method, we will get the descriptive statistics of our features. If we want to include only the numerical features, we can remove the input parameter include, and that way we will get descriptive statistics only for the numerical features. If we use the describe method with the input include equals to all, then we will have the descriptive statistics of all our features. Here we can see the mean value, the minimum value, the maximum value, and so on. For this example, we will try to find if a client has deposit or not. That is the last column that is contained in our dataset. An easy way to check for missing values is to use the method isNull. This method will return a data frame with true and false values. And if we sum these values, we can see in which column we have missing values. In this example, we can see that we have missing values in the column age, balance, and contact. There are two approaches for handling missing values. The first one is eliminate. If we have 5% or less of the data that is missing, we can eliminate the rows that contain missing values. So in Python, this is done by using the function drop. Also, we can eliminate the columns with missing values. If the column has 95% or more missing values, it can be removed because the estimation will be calculated based on the 5% or less of the data. So this column can be removed. In this example, contact column doesn't have 95% of the data that is missing, but it is removed just to explain the procedure. The second approach is estimating the missing values. We can estimate the missing values by using the simple imputer. This means that we will estimate the values by using the mean, the median, or the most frequent value of the respective feature. Estimation is performed only if acceptable percentage of values are missing. In this example, we can see a simple imputer, and this way we are filling the missing values with the mean value of the respective feature. Also, we can use the mice method for estimating the missing values. This is the most this is the most used method for imputing the missing values. MI stands for Multiplevariate Imputation by chain equation. This is a robust informative method of dealing with missing data in a dataset. The procedure fills in missing data in a dataset through an iterative series of predictive models. In each iteration, each specified variable in the dataset is imputed using the other variables in our dataset. This process is continued until all the specified variables have been imputed. Additional iterations can be run if it appears that the average imputed values have not converged, or although no more than 5 iterations are usually needed. The accuracy of the imputations will depend on the information density in our dataset. A dataset of completely independent variable with no correlation will not yield an accurate imputation. In Python, we can use the package fancy impute. And here we have iterative imputer. This is the mice imputer that I already explained. In this example, we can see that we are performing some imputation in the column age. And after this, we won't have any missing values in our dataset. If we are working with regression, this is a very important topic. Outliers are observations that lie on abnormal distance from the other observations in the data. Why this is a problem? They affect the regression dramatically because the regression will try to place the line closer to the outliers. If we have a normally distributed values, we are expecting that 68% of the data is distributed in the interval of the mean minus standard deviation and mean plus standard deviation. 95% of the data is distributed in the interval of mean minus 2 standard deviation and mean plus 2 standard deviation. And 99.7% of the data is distributed in the interval of mean minus 3 standard deviation and mean plus 3 standard deviation. If we try to plot the distribution for one feature of our dataset, for an optimal result, we are looking for a normal distribution. But as we can see in the picture, this is not a normal distribution, and we can say that we might have outliers. So, as I mentioned, the problem with the outliers are a problem if we are using a regression. And now we will try to remove the outliers. The outliers are all the values that are out of the third interval that I mentioned before. And after removing those values, we can see the distribution is still not normal, but it is acceptably closer. And also the mean value, the maximum value, is closer to the mean value. Now we can say that we have less outliers. We can do this with multiple features from our dataset. Multiculinarity is sometimes also a problem. Multiculinarity exists whenever an independent variable is highly correlated with one or more of the other independent variables in a multiple regression equation. Multiculinarity is a problem because it undermines the statistical significance of an independent variable. One of the best ways to check for multiculinarity is through variance inflation factor. Variance inflation factor produces a measure which estimates how much larger the square root of the standard error of an estimate is compared to a situation when the variable was not correlated with the other predictors. The numerical feature for variance inflation factor tells us what percentage the variance is inflated for each coefficient. For example, if we have a variance inflation factor of 1.9, this tells us that the variance of the particular coefficient is 90% bigger than what we would expect if there was no multiculinarity. When we have a variance inflation value equal to 1, we can say that there is no multiculinarity at all. Values between 1 and 5 are considered as perfectly okay, but we cannot find a strict definition of which values are acceptable. Sometimes maybe values below 5, 6, or even 10 are acceptable. In Python, we can use the package stats model, and then we can compute the variance inflation factor. We can see that in our example, all the values for the variance inflation factor are below 5, and we can say that they are okay. We can rarely find data where all the features have values below 5. We can say that in our data set we don't have multiculinarity. If we had multiculinarity, we should drop the column that has a high value of variance inflation factor, and this can be done by using the method drop in Python. In almost every dataset, we have categorical features. Dummy coding is a commonly used method for converting categorical input into a continuous one. Dummy, as the name suggests, is a duplicate variable which represents one level of a categorical variable. Presence of a level is represented by 1 and absence is represented by 0. For every level present, one dummy variable will be created. And also we can see on the picture on the picture above that we have 3 categories. Then we are by using the dummy get dummies in Python, we will have 3 more columns. And if the row belongs to the first one, we will have value 1, and if it doesn't, we will have value 0. Actually, get dummies, the method get dummies converts the new data frame, our data frame, into a new data frame that contains one hot encoded columns. This is actually called one hot encoded. A common problem that we may encounter is unbalanced data set. This means that the target variable has more observations in one specific class than the other. If there is a very high difference between the positive values and the negative values, we can say that our dataset is unbalanced. On the other hand, balanced dataset means that positive values are approximately the same as negative values. We can see an example on the picture below. On the left picture, we can see that we have less red points than the blue ones. So we can say that this dataset is unbalanced. And on the right side, we can see that we have approximately the same number of orange and blue points. And we can say that this dataset is balanced. Imbalanced dataset is one of the potential problems in the field of data mining and machine learning. This problem can be approached by properly analyzing the data. A few approaches that can help us tackling the problem at the data point level are undersampling and oversampling. Also, there are more complex methods of handling the imbalanced dataset. Here on the slide, we can see 2 approaches of balancing the dataset. The first one is oversampling. This means that we will extend our minority to be the same size as our majority. Advantages of this approach are that we have no loss of information, and we mitigate overfitting caused by oversampling. But the disadvantage is that we might have overfitting. The second approach is undersampling. This means that we will cut our majority to be the same size as our minority. Advantages of this approach are that runtime can be improved by decreasing the amount of training dataset, and also it helps in solving the memory problems. But the disadvantage is that we might lose some critical informations. In this example, we have undersampling, cutting the majority to be the same size as a minority. We are removing some points from the majority, and that way we are balancing our dataset. In Python, this can be done by using a for cycle and inserting the indices that should be removed. And after that, using the list that we defined with the indices, we can remove the rows from our dataset. Perhaps the most widely used approach to create a new examples is called smooth or synthetic minority oversampling technique. It works by selecting examples that are close to the feature space, drawing a line between the examples in the feature space, and drawing a new sample at a point along that line. Specifically, a random example from the minority class first is chosen. Then k of the nearest neighbors for that example are found. Typically, k is equal to 5. Usually, we use that value for k. A randomly selected neighbor is chosen, and a synthetic example is created at a randomly selected point between the two examples in the feature space. This procedure can be used to create as many synthetic examples for the minority class as are required. One of the ways to use smooth is first randomly undersample the number of examples in the majority class, and then use smooth to oversample the minority class to balance the class distribution. Here on the picture, we can see an example of unbalanced data set. We can see that we have more blue points than the orange ones, so we need to balance our data set. In this example, I used the package IMBlearn and the module smooth. After applying the smooth method, we can see that our data set now is balanced. The green and the blue points are the same, but the orange points are now more. And by using this technique, we balanced our data set. After balancing the data set, we need to standardize or normalize the features. The question is always when we should use standardization and when normalization. Standardization assumes that the data has a Gaussian distribution. This does not strictly have to be true, but the technique is more effective when the distribution of the attribute is Gaussian. Standardization is useful when the data has varying scales, and the algorithm that we are using does make assumptions about the data having a Gaussian distribution. And these algorithms are linear regression, logistic regression, and linear discriminant analysis. Standardizing the features means that we will scale the feature, and after this, the feature will have a mean value equal to 0 and standard deviation equal to 1. Variables that are measured at different scales do not contribute equally to the analysis and might end up creating a bias. For example, we might have a variable that ranges between 0 and 1000, and that variable will outweigh a variable that ranges between 0 and 1. Normalization as well is a good technique to use when we do not know the distribution of the data or when we know that the distribution is not Gaussian. Normalization is useful when the data has varying scales and the algorithm that we use does not make assumptions about the distribution of the data. For example, k-nearest neighbors or neural networks. The goal of the normalization is to change the values of numerical columns in the data set to a common scale without distorting differences in the ranges of values. Yes, I saw the question. I can provide some materials. Yes. Yes. Can I answer the data preprocessing gone wrong at the end? Yes, I will answer the second question at the end. Yes. For machine learning, every data set does not require normalization. It is required only when we have features that are on a different ranges. For example, we have a feature that ranges from 0 to 100, for example, age. But we have another feature, for example, income, and it ranges from 0 to 100,000. We can say that these two features are on different ranges. When we do further analysis, we can see that that attribute that has larger values will have more weight. So, but this doesn't mean that that feature is more important to our prediction than the other one. So we will normalize the features and they will be on the same scale, and we will avoid this issue. Also, it is good if we shuffle the data. Shuffling algorithms randomly shuffle data from a data set in one column or a set of columns. By shuffling the data, we ensure that each data point creates an independent change on the model without being biased by the same points before them. In Python, we can use the package NumPy and randomly shuffle our dataset. The last step of the data preprocessing is splitting the data into test and train set. The training set contains a known output, and the model learns on this data how to be generalized to other data later on. If we have very high accuracy in the training set, that's not good because we might have overfitting when we create a model. What does mean overfitting? That means that our model won't be generalized for other data sets. Also, we have our test set. This is a set that will be used to test our model's prediction. In Python, we can use the module train test split in order to make the split. The test size 0.2 as an input parameter indicates the percentage of the data that should be held over for testing. This split is usually around 80-20 or 70-30. Now we can build a machine learning model. We want to predict if the client has deposit or not. So because of this, we will use a logistic regression. In statistics, logistic regression model is used to model the probability of a certain class or event existing, such as pass-fail, win-lose, alive-dead, or healthy-sick. In machine learning, logistic regression is defined as a supervised machine learning algorithm, and it is used to predict the probability of a target variable. The nature of the target variable is dichotomous, which means that it will have only two possible classes. In simple words, the dependent variable will have two values coded as either 1, which stands for success or yes, or 0, which stands for failure or no. Here we can see how we can train the model using scikit-learn and the module logistic regression. We will create an object from this class, and we will fit our train set. Previously, we divided our data set into training and testing. So in this, here in the fit method, we will use the train inputs and train targets in order to train our model. Also, after this, we will use the test set to test how our model performs. The next step is building the confusion matrix, and we can use these values to see how many of the given inputs are not predicted correctly. More specifically, we can see how many values are false negative and false positive, and how many of them are true positive and true negative. Here on the left side, we can see the confusion matrix. Here we expect the true negatives, and here the false negatives. This means that the predicted value is 0, but the actual value is 1. This in Python can be done by using the module confusion matrix from sklearn, and on the bottom we can see the results of our model. The last step is calculating the precision, the recall, and the F measure. Precision quantifies the number of positive class predictions that actually belong to the positive class, and recall quantifies the number of positive class made out of all positive examples in our data set. F measure provides a single score that balances both the concerns of precision and recall in one number. False positives and false negatives can be crucial to the study, while true negatives are often less important to some problem that we are trying to solve. The F-Eden score tries to take this into account, giving more weight to the false negatives and false positive, while not letting large number of true negatives influence the score. So those were some of the data preprocessing techniques. As a conclusion, I would like to say that machine learning denotes a step forward in how computers can learn and make predictions. It has applications in various sectors and is being extensively used everywhere. Applying machine learning and analytics more widely let us respond more quickly to dynamic situations and get greater value for our fast-growing troves of data. Machine learning has been gaining popularity since it came into the picture, and it won't stop anytime soon. Thanks for your attention.